Now let me define another parameter which is called the force transmissibility. Which is how much force is transmitted from the base to the mass. We call that the free body diagram. We had a spring mass and a damping spring force and damping force, Cx dot minus y dot. So this is the force applied by the moving base to the mass. So F transmitted is Kx minus y plus Cx dot minus y dot. But again, going back to the Newton's balance equation, the second law, which means that the sum of forces is equal to ma. The sum of forces was negative k x minus y, negative c x dot minus y dot equals ma, which is mx double dot. Which means that this term, the force applied, is actually the negative of mx double dot. Mx double dot. Okay. Now, the amplitude or the motion x of t was x cosine omega b t minus theta minus phi, which means that x double dot is negative omega b squared x cosine omega b t minus theta minus phi. Okay. So the amplitude then of the transmitted force Ft is m times the acceleration. Both are negative, so I'll use the negative sign, and it will be m times omega b squared x. But recall that x over y, the distance transmissibility, or the amplitude x itself, was y times 1 minus 2 zeta r squared plus divided by 1 minus r squared all squared plus 2 zeta r all squared all under square root. Okay. So now substituting this into the force transmissibility, or the transmitted force actually, I will have F transmitted equal m omega b squared times y times the square root of 1 plus 2 zeta r squared 1 minus r squared all squared plus 2 zeta r squared. Now, k over m omega n squared equals k over m, which means that m is k divided by omega n squared. So let me use this and substitute for m over here. Okay. I would have k y omega b squared divided by omega n squared 1 plus 2 zeta r squared 1 minus r squared all squared plus 2 zeta r all squared under square root, and omega b divided by omega n is r squared. So f transmitted divided by k y is, what's left here is r squared and the square root term 1 plus 2 zeta r squared 1 minus r squared all squared plus 2 zeta r squared under square root, and this is the what's called the force transmissibility, which is how much force is applied to the system by the motion of the base compared to the force, string force, where that's equivalent to a displacement y, the amplitude of the motion of the base. This is of course a dimensionless parameter because it's force divided by ky, which is a force also. Now, just like in the distance transmissibility, we determined that this fraction has a value of 1 when r equals square root of 2. This was the distance transmissibility, just this fraction, and we noticed that the distance transmissibility was 1 for all damping when r was the frequency ratio square root of 2. Now, this is 1 for r square root of 2. That means that transmissibility is r squared, which means that this is equal to r squared, which is 2. That's only when r is equal to square root of 2. The force transmissibility will always be 2 at r equals square root of 2, as opposed to the distance transmissibility, which was 1. So now, if I plot this force transmissibility versus the frequency ratio, r ft divided by ky, I will notice two things. First, that for r equals 0, the force transmissibility starts at 0, okay, goes up to infinity for zeta equals 0, but then this is 1, this is 2, it will go down to some value other than 1 at square root of 2. Now, if you add more damping to the system, go to a higher value, but then pass through the same point, and so on. And then for overdamped systems, so the final value of the force transmissibility is not always the same. It changes depending on the damping ratio. Okay, this is zeta 0, this is overdamped, and these are intermediate values of zeta, let's say 0.5 or 0.7. They all produce force transmissibility of 2 at square root of 2 ratio, and the resonance happens at or near r equals 1.